Hey there, we're back to wrap up the binary tree mechanism, and uh, after much waiting, we're finally going to see what this mechanism is. So I want to start by just giving a sense of what types of improvements we could get over the simple improvement we saw where we replaced interval queries with just the kind of one-sided interval queries. So here's a way of doing some accounting to see why we were able to improve. So we started with a baseline algorithm where we had about d squared queries, and their sensitivity was thus d squared at most. And in order to get all the answers we wanted, we didn't have to do any combining. We just looked up the answers. So we added noise to each query, and that was the only noise we got in the answer. And so the error was about d squared log d. I'm going to ignore epsilon because it's going to be the same for everything else. We improved by finding actually a subset of the queries, about just d queries. And because there's only d queries, the sensitivity was dropped down to d. And the only thing that got worse is that now if we wanted to answer an interval query, we might have to combine two of the queries in our subset. And so the error for each query was d log d. We multiplied it by 2 when we combined, so we overall get still d log d. So now what we're going to do is we're going to see the binary tree mechanism. And it's going to be based on the same template. We're going to find a subset of queries we're going to combine. And, the first thing you might guess is that we just find a smaller set of queries, but that's not true. We're actually going to answer about 2D queries, 2D intervals. That seems worse. So where are we going to win? Well, the sensitivity of these queries is going to be much lower. We're going to choose these queries very carefully so that the sensitivity of the queries drops to about log d. Okay, so that's going to be our big win because now, even though there's lots of queries, if I write them down as one vector, the total sensitivity of that vector is only about log d, so I can add noise proportional to about log d. So each of those queries is going to get noise that's about log squared d, if you work it out. But how am I going to combine? Well, it's going to be a little worse. So I'm not going to be able to get an answer to any interval query by combining 2. I'll have to combine about log d different answers in order to get the remaining interval queries. And when we put it all together, this is going to come out to about log cubed of d as the final error. Okay, so that's a big win. We're going all the way from d log d down to log cubed of d. Obviously, the cubed is a little undesirable, but going down from d log d to log cubed d is a big win. And in fact, even at modest sizes, this is a big win. So, okay, this is what we're kind of shooting for. All right, I haven't really told you how we do anything, but this is sort of the idea. Is we want to find a bunch of queries, about d of them, and we want the whole the sensitivity of the queries to be a lot lower than their number. Okay, so just remember what that means is that it's going to have to be the case that changing one data point cannot change the answer to all of these queries. It has to have a kind of limited effect. So the queries are going to have some very special structure. And here's how we're going to construct the queries. So remember, here's a depiction of my data set if the domain is d equals 8. So d equals 8. And I'm going to assume d is a power of 2 for reasons that is going to help. Okay, it's going to be sort of obvious why I want to assume that, but of course, if it's not true, I can just increase d to the nearest power of 2, and that'll at most double d, which is not going to make a big difference. So what am I going to do? What are my queries going to be? So all my queries are going to be interval queries. Okay, that's not a requirement. There's nothing that says we have to ask a subset of the interval queries, but that's just going to be the case. So I'm going to pick a subset of queries, and I'm going to pick the queries as follows. I'm going to start by just asking for all the intervals of length 1. Okay, so I'm just going to ask for all these intervals. And for reasons that might become clear, I'll think of these as nodes in a graph, and I'll draw them as circles. Okay, so this is going to be all queries, intervals. They're interval queries. of length 1. Okay, and I can write down the answers to all these queries. 3, 0, 2, 0, 2, 1, 4, 7, just to give you like a sense of, what these queries mean. So this is not going to help me. Okay, so here's a good thing about this. The sensitivity is 2. If I change one of these purple points, I can add 1 and subtract 1. I add 1 to one of the queries and I subtract 1 from one of the queries. So this is just a histogram. Its sensitivity is 2. But if I want to come up with some interval query, like, if I want to answer how many people are between 1 and 8, I have to sum up 8 of these. Okay, and that's going to hurt my error a lot. Like I might have to sum up d of these in order to get an answer to a query. So I'm not out of the woods yet. Right? So the problem is if I want to ask about a big interval, I have to sum up like lots of these things. So let's try asking some queries about bigger intervals, and maybe that'll help a little. So what we'll do is we'll add a query for every interval of length, for like consecutive intervals of length 2. Okay, so not all intervals of length 2, but I'll just take, interval from 1 to 2, 3 to 4, 5 to 6, 7 to 8. So I'll just take a set of consecutive intervals of length 2. And of course, each of these queries is like summing up 2 of the queries of length 1. Oh, sorry, why did I put 7 there? Right, so each of these queries is just summing up the 2 nodes above it. Okay, maybe you can start to see where the binary tree idea is coming, because I've got these little individual binary trees of depth 2. All right, so now, I'm helping a little. Like if I want to answer the query, how many people are between 1 and 8, I don't have to sum 8 queries, I have to sum 4. So it's like kind of not enough, right? Like that's not helping enough. I still have to sum d over 2 of these queries. So let's try now, building all the, consecutive intervals of length 4. Okay, so this one has answer 5, this one has answer 10. And now, if I want to get an answer to the query, how many people are between 1 and 8, I only have to sum up 2 of these queries, which is starting to look good. But of course, in general, I have to sum up d over 4 queries, which is still a lot. So let's just keep going until we go all the way up the tree, and we just get a single query. All right, and now, so, obviously at the top, I just got one query whose answer is n, but at the end, we get, one interval of length d. Okay, so the number of times I have to do this is logarithmic, right? If there's d, if the domain size is d, this tree is going to have depth log base 2 of d. Okay, so tree has depth log base 2 of d. Number of queries / nodes in the tree is, I think, 2d minus 1. Okay, so in this tree, there's 15 nodes. Okay, so I've picked my subset. The subset I'm going to ask are the nodes of the binary tree. All right, or, it's going to be like all the intervals of length 1. Then it's going to be, I'm going to split my line into intervals of length 2. Then I'm going to split my line into intervals of length 4, and then length 8, and then length 10. Or then length 16, and I'm going to do this all the way up to length d when I get just one interval. All right. So let's kind of think for a second about so the number of queries is 2d minus 1. What's the sensitivity of these queries? All right, so suppose I add a single data point. Okay, so suppose I add a 4. All right, well, which queries does this 4 impact? Well, it impacts this query, which is asking for just the interval 4. It also impacts its parent in the tree, which is asking for 3 and 4. And it also impacts that parent in the tree, which is asking for 1 through 4. And finally, it impacts that parent, which is asking for 1 through 8. And then we're done. So if I add a data point, the only queries whose answers change are the queries in the path from the leaf in the tree up to the root. And there's exactly log base 2 of d such queries whose answer I actually change. All right, and that's like a very special property of how these queries are constructed, right? It's the fact that there's log base 2 of d layers, and in each layer, only one query can possibly have its answer changed. Now, of course, I don't just add a data point. We want to talk about adjacent data sets where I change something. So maybe what I actually did was I moved this data point over here. And so I also subtracted something from these queries, which are on some other path from the leaf. Okay, so here I did +1, +1, +1. Here I did -1, -1, -1. And here I did like +1, -1, which is 0. So I never changed that. So what's the total sensitivity? Well, it's all of the red squared nodes. And the number of nodes that are red, where I change the answer, is going to be 2 at most. I should say at most. It's going to be at most 2 log base 2 of d minus 1. Okay, so it can be smaller because it could be that these two paths actually meet somewhere closer, they meet before they get to the root. But kind of the worst case is that they meet up at the root of the tree, or as I drew it, down at the root of the tree. And if they meet down at the root of the tree, then there'll be pluses and minuses, pluses or minuses on 2 log d minus 1 nodes. Okay, so let me copy this for later. Okay, good. So that's the sensitivity. And now what does that mean? Well, that means that the error, if we answer all these queries with independent Laplace noise calibrated to the sensitivity, is proportional to 1 over epsilon log squared of d. Okay, now why do I get log squared of d? The standard deviation of each Laplace variable is log of d, but there's about d of them, and so the log of the number of queries is another factor of log d. So I get log squared of d. And this is just by our standard analysis of the Laplace mechanism. If this is going by a little quickly, I recommend just kind of recapping the Laplace mechanism and what is the error going to be if I add a Laplace random variable with a particular scale to some large number of times. What's the largest error I'll get? Okay, so far, what have we said? We said I have this special subset of queries, and I can answer these queries where the error on every query is at most log squared of d. Okay, but I care about queries that are not in this tree, right? What if I want to answer the query, how many people live between 1 and 7, right? What do I do? I don't have, that's not one of the queries I answered. And that's where we're going to do some kind of clever reconstruction. So let me do a little slide maintenance. Oops, I wanted like more than that. Let me do a little slide maintenance. Copy, paste, and let's get rid of this stuff. Should have some hold music while I do this, a little smooth jazz. So, all right, how am I going to get the answers to queries that I don't already know the answer to? Well, suppose I want, f1 through 7. Okay, so f1 through 7, that is, this query. And I'm going to start by only thinking about queries of the form 1 comma t, because as we said, if I can do all the queries of the form 1 comma t, I can combine 2 of those to get queries of the form s comma t. So how am I going to get 1 through 7? Well, let's just kind of greedily start by picking like the biggest interval we can. So 1 through 7 contains this interval, right? This is f1 through 4. So I've got like f1 through 4. Okay. And it also contains, now I only have to do 5, 6, and 7. So let's look at 5, 6, and 7. What's the biggest interval that contains? Well, it's this one, 5 through 6. Okay, so that gives me 5 and 6. And now I'm left with just 7. And the biggest interval that contains is 7. Okay, so what have I done? I said, I can write f1 through 7 as f1 through 4 plus f5 through 6 plus f7 through 7. Okay, so I'm just summing up 3 of these random variables, and so I'm increasing the noise by 3. Whoops. All right, more generally, here's a key fact. For every t, f1 through t is the sum of, at most, log d queries in the tree. So most log d queries in the tree. All right, and this is like the key fact. All right, so this is going to be, it's an exercise in the lecture notes. It'll probably be an in-class problem to prove it. But the intuition is that I should only be summing up 1 interval from each level. If I'm ever summing up 2 intervals from some level, I could do better by just like combining them. That's kind of the rough intuition. All right, and there's just a simple algorithm that if I ask for the interval f1 through t, then there is a simple way of finding which intervals to sum up. In fact, it's just the greedy algorithm. So I ask, should I take the root? Is the root contained in the interval I want? No. So go to the next layer. Is one of those things contained? So in this case, yes, f1 through 4 is contained. So add it, and now kind of recurse on 5, 6, and 7. What's the biggest interval contained in 5 through 7? It's 5 through 6, and so on. So there's sort of just a simple like greedy algorithm for finding the right thing. All right, and that's the last piece we were missing. So we said that we can answer every node in the tree. We get an answer with error log squared d. Then we sum up the answers over all the log d nodes in the tree. We get log cubed d. All right, and the last little small piece that was missing, right, is that for every st pair where we don't, s is not 1, we have fst equals f1t minus f1s minus 1. And so if you kind of unroll these two statements, you get that for every interval query, I can write it as like a sum of log d queries in the tree minus a sum of, minus some other log d queries in the tree. So I'm taking, 2 log d different errors. Okay, so it doesn't affect things by more than a constant. All right, and that's it. That's the whole theorem. There's a little, there's a few details to fill in here of, if you wanted to actually code this up, you would have to like think of exactly how you represent the nodes in the tree, which things you're counting, and then maybe more importantly, if you want to figure out how to recover the answers, you have to sort of fill in the gaps in the statement I just made, that there's always a way to sum up logarithmically many answers to get the intervals you want. And the final result we get is that the binary tree mechanism answers all interval queries in a domain of integers 1 through d with expected maximum error 1 over epsilon times log cubed of d. Right, and one thing I should also add is that this analysis was a little bit loose in how we did it. You can improve the error a little bit, so it can be a slightly smaller exponent than 3. But that's not really the point I wanted to emphasize. What I want to emphasize is that this was a very clever way of getting the error down from proportional to d to just polylogarithmic in d. All right, so we're almost done. I just want to conclude with a couple thoughts. So the first is basically about the question of what is this parameter d? So maybe if I have ages measured in years, d is 126. There's 126 integer years you can be, 0 through 125, roughly. But age is of course a continuous thing. It's not actually measured only in years. You can measure it in days. You can, in principle, measure it in seconds and fractions of a second. So sometimes d is not given, but actually not given, but chosen. Okay, so we actually might have your exact birth date, so we know your age in days. Maybe we don't know more than that. So there's the set of days, it's 125 times 300 something. It's a lot. It's on the order of I don't know, 100,000. So d might be too really big. We don't want d to be that big, so we decide, all right, let's do years. And that might be good enough for certain things, but if we're looking at the age of preschoolers, their ages in years are up 0 through 4, so we're probably losing a lot of information. We really want to know their age in weeks maybe. So depending on what the data looks like, the data is, we can sort of trade off kind of granularity versus error. All right, so depending on what the actual, depending on what the actual data looks like, we might want to we might want to choose a different way of representing the data as integers. So maybe we want to represent it as an integer number of weeks, or an integer number of months, or an integer number of years, and different choices are going to coarsen the data. We're going to lose granularity, but we're also going to make d smaller and get better error. So that there's often, this is actually something you have to choose, and choosing it is actually quite tricky. Okay, so choosing it's a pain. So one question you might have is, maybe it would be easier to choose if we didn't have to have an algorithm whose error depends on d at all. Maybe we can just have an algorithm whose error, who just works directly with real numbers. We don't have to actually discretize the data to integers at all. Or maybe we can just get a much better trade-off on d so that we can do a higher granularity. We get better trade-offs between granularity and error. And actually we can. There's lots more algorithms for this problem using some very clever ideas. So I'm not going to describe how they work, but there are improvements that give error roughly log d plus log cubed of n. So now we have different parameters here, but if n is much, much smaller than d, right? If d is a big domain, but if d is like ages in minutes, but most distinct numbers of minutes are not represented in our data set, we get error growing more with the number of people in the data set, not the potentially huge domain size d. So this is some improvement. And in fact, there's been a lot more improvement on this. And in fact, you can get this down to some, sort of ridiculous looking error bound, which is the log star function of d to the power of 3/2 plus log cubed n. So almost independent of D. You may not know what this log star function is. If you've never seen it, go look it up. It's a fun function. And the gist is that it is an extremely slowly growing function of D. So it barely grows as D goes to infinity, but it does go to infinity with D. Okay, so it's almost down to D. And you might say, look, surely at this point we should just be able to get error that doesn't depend on D at all, but that's not true. Every algorithm that's private has error kind of proportional to this log star. So in particular, I mean, this is a very surprising fact. In particular, there's no algorithm that just works for all reals. There's no algorithm that can answer all interval queries or compute a cumulative distribution function, or even be guaranteed to compute the median if the domain of your data is all reals. So we have to do some kind of discretization, and how to do this discretization is actually kind of a significant question in practice. So unfortunately, in order to do something even fairly simple like compute just these interval queries with differential privacy, we suddenly can't just work with real numbers. We have to work with discretized numbers, and we have to pay something for that discretization. So how to prove this is sort of beyond what we're going to do in the course. It's a really beautiful proof. It's really quite a surprising fact. I just want to emphasize basically that there's been a lot of work on these interval queries. A lot of nice ideas have come out of that work, and a lot of interesting kind of phenomena come up in differential privacy by studying this problem, like the fact that to solve problems with differential privacy, we often need to do some kind of discretization of the domain that we wouldn't need to do if we were working without, if we didn't care about privacy. All right, and the last point I want to make is that what we really did here is we answered all the queries with the binary tree, and we post-processed those answers in some way. And because of differential privacy's properties, we can post-process them in any way we want. And there's actually been a lot of ways that say there's even better ways to combine than just summing up some nodes in the tree. So there's even better ways to combine answers. And the nice thing about privacy is it says basically once you pick what you measure, so once you pick the queries you're going to answer with privacy, you can do whatever you want to recover better answers. You can get sort of as clever as you want without having to think about privacy. And so just, one of the nice things about differential privacy is that that's something you can do. You don't have to change the analysis if you come up with a better way of combining answers. So that's it for today. I'll leave you with this very cool binary tree mechanism and my super fancy pictures that I drew throughout the lecture, and I will see you in class. Thank you.